Okay, I started. Okay, thing is an important topic for heat transfer in industry. You really a lot of times you have to manage the heat. Okay, all kind of industry, whatever manufacturer generate heat. Okay, heat is usually a not good thing, so you have to manage it and then remove it. Okay, so sometimes you want to collect it and to generate the power also, right? So thing is a device that commonly used in industry to remove heat from a surface. Okay, so it's important. Sometimes in the process you don't want it to be too hot, right? So that's why we need to remove the heat. If you open a computer, even you see that the little fan on top of the CPU to remove heat. Some of the microchips, they have the fin structures on top of it first, and in addition with the fins, okay, to remove the heat. So the mechanism, as a review for last time, okay, the mechanism for removing heat is very simple for the fin, okay? It's just basically increase the surface area, okay? By adding a fin on a surface, you add surface areas because of the fins, you know, that's additional surface area. If you have more surface area, you remove heat more, okay? That's the major mechanism for removing heat transfer in the fin application. Okay, but that's for the regular size fins. Okay, the flow, the fin actually alter the flow a little bit, right? You usually you blow air to cool down some surface, but when you're adding the fins, you change the flow a little bit near the surface. So the convection heat transfer coefficient could be changed. Okay, so the heat transfer, the convection heat transfer initially without the fin could be different compared to with fin. Although the fin increase the heat transfer by increasing the surface area, but it might reduce the flow near the surface. So it might decrease the heat transfer a little bit. So when you do the design, sometimes you need to consider that. Okay, I can say that in the regular size application, you know, the alternation of the flow, the effect could be much smaller. Okay, and the increase of the fin area will have more dominant effect. So you will have, you know, net gain of heat transfer. Okay, but if the thing is not that efficient or effective, later today we're going to talk about the efficiency and effectiveness. If it's not that really effective, then it increased the heat transfer a little bit, but it decreased heat transfer due to the presence of the fin structure. Okay, it's possible. So that kind of design you have to avoid. Okay, because basically it's useless or even getting worse. Okay, that's a regular size thing. For the very small size things, for sometimes you use it called the micro things, microstructures on the surface. Okay, so you know, in the 21st century engineering design, sometimes we have to do with very, very tiny, small designs, right? Small structures. Okay, you also need to do heat transfer, use fins. So the thing could be very, very tiny, micro thing they call it, if it's not nano thing. Okay, micro things. Then in those applications, the increase of the surface area is tiny. It's very, very little. So the effect from the increasing of surface area could be very small, okay? But in those applications, the surface roughness could have significant effect on altering the turbulence near the surface, okay? You see, microfilm is just like a rough surface, okay? Constructed rough surface, right? Microfilm. Okay, so you know when the flow over a smooth surface and a flow over a rough surface, the turbulence characteristics are totally different. Okay, some of the turbulence really, really helpful for transfer heat. imagine there are small eddies, turbulence created near the surface. Okay, then those eddies travel really fast into the main flow. When there's structure travel like that, it's like a vortex, right? Eddies, like a tiny hurricane, okay, starting from the wall. When it go away from the wall, it carries significant amount of heat, okay? So the constructed rough surface may help enhance the small scale turbulences, okay? Therefore, it might enhance the heat transfer because the turbulence, when it flow away from the wall, it carry heat away. So that's a different mechanism for fin, for heat transfer and for the fin. When you look at a very, very small structure, small micro fins. Okay, so keep in mind, this is not in the textbook. Okay, so I think textbook, you just talk about the size of the, you know, bigger size things, okay, regular size things, okay, and not mentioning the small size thing. And if it's a small size thing, it's the mechanism is really different. It's the changing the flow that causing the heat transfer, okay, causing the changing of heat transfer. But for the regular size, larger size things like what we discussed in the textbook, the major mechanism is the increase of the surface area. Okay, most of the time, the bigger thing like this, it will decrease the flow. Actually, it's not good for the convection heat transfer itself, but because of the larger surface area, that effect is, you know, more significant. So it have a net gain of the heat transfer. Okay, just keep in mind. Okay, but fin is really important. In heat transfer, hey, what kind of things we learn? Basically, fin is one of the major things, right? Heat, and then maybe later is heat exchanger is another topic, practical. Fin is one of them, okay. Okay, so some background introductions. Let's look at my screen now. Let me share my whiteboard. Okay, so what we did last time. So we talk about case 1, case 2, case 3, right? There are three. By the way, anybody can see my screen? Is that good?
We can see it.
Okay, yeah. Now, since the difficulty last week, right? Now, every time I'm gonna ask you if you see my screen clearly, okay, when I'm recording it. Okay, so last time we talked about the 3 types of the things, case 1, case 2, type 1, type 2, type 3, right? Each type, okay, we have the solution for temperature distribution inside the thing, okay? So as well as the total heat lost by that thing, okay? The heat loss is good, right? The more heat loss, the better the thing is, okay? So Q. So we have 2 sets of solutions basically for each case, case 1, case 2, and case 3. One equation is for theta. Remember what is theta? Anybody? It's a review. You don't need to look at
change in temperature.
Yeah, it's a change of it is temperature, right? A change of temperature. It's a relative temperature, right? With the reference of what? What temperature is your reference temperature in theta?
I think it's.
Anybody remember? So theta must be a t, right? Okay, of course it's a t. T is the variable. Inside the fin, t changes with along the fin direction, okay? So t is a variable, okay? T minus what? So it's a reference temperature, right? Theta is a reference temperature. T minus
T infinite, the temperature of the surrounding.
Let's look at the definition. Yes, you are absolutely right. Theta is T minus T infinite, the surrounding temperature, right? Obviously, we use the surrounding temperature as our reference to see how high the temperature is comparing to the ambient temperature, okay? So what is theta 0? Anybody? theta 0. So it must be referenced with the same ambient temperature, right? Something minus T infinite too. What's minus T infinite? It's 0, right? It's T naught, right? T naught, what is T naught then?
That's the temperature right in the middle of whatever.
No, it's not the heat source problem.
Oh
The
my
thing,
god.
right? Yeah, it is
Yeah.
the base temperature.
It's at the base. Yeah.
Yes, yes, yes. The T0, we use the base. Obviously, that should be the temperature we know, right? T0. It's without the thing, basically. What should be the temperature on the wall, right? So the base temperature minus the T infinite. Okay, so just try to understand. This is basically a simplified version of the temperature equation, right? Just want to use theta, look a little bit simpler. Okay, well, no, equation is long. We always want to be shorter equation. Okay, when write on paper, it will be simple to write. Okay, that will be good, right?
So
Okay.
Dr. Zhang,
Yeah.
for all these cases, we have theta over theta naught. What's the significance of theta over theta naught?
Oh, that's the temperature distribution. You need to know that what's temperature inside the thing. The thing is a long, it's not long, it's a structure, right? The temperature inside the thing is changing. Do you agree?
Yes.
Okay, so inside the thing, in the base, the thing have T naught, which is the highest temperature. Okay, so the temperature will decrease inside the thing, right?
Right.
Okay, what is where is the lowest temperature in the thing?
The end of the fin.
The end of the thing. Okay, so based on this equation, you see, for example, I'm showing this case 1, for example, this is the equation, okay? So you will be able to find the temperature in terms of x. X is the thing direction. Is that right? Based on this, hey, every location, if I want to find the middle of the thing, what is the temperature? Okay, here we go. Middle, x, you have a value in the middle, right? Okay, based on that x, you should be able to find your t. Does that make sense?
Yeah, it makes sense.
Okay, so this is a temperature distribution inside the thing. Very, very useful. So you should be able to find, hey, this maybe you can do a project like this. You should be able to find the temperature any location on that thing, okay, as long as you can measure the distance to the base, okay, based on this equation, right? So this is the temperature, and then it's a Q. Remember, the total Q, the loss of the Q is through the side area of the thing, the entire area of the thing. Okay, so that's the total. That's important information to obtain, because you want to know for each thing how much heat it can transfer, it can remove. Okay. So these are the use of the equation. Now, in this class, heat transfer, I'm teaching heat transfer and the fluids all together. It's different. The fluids, you have a lot of equations, you have derivation, you have to know those equations, how they're coming from, what is the physics behind. Here, the equation in heat transfer, so those equations become so complicated. So you basically, what we do is we skipped all the derivation here. So, but you have like a way more equations than in the fluids class, 10 times more maybe. Okay. So for each equation, you really need to know those equations, what the equation for, okay? For a certain situation, you need to able to pick a correct equation to solve for that situation, okay? So that's the kind of different between, in fluids, maybe the entire class, you have maybe 10 equations, 15 equations, that's it. Here you have like a bunch of equations, much more, okay? So, but here in heat transfer, since the problem is more complicated, then you basically, we skipped all the derivation, where the equation coming from, and why the equation look like this. Okay, this part is too complicated. Let's leave it to the graduate school. So, but we have too many equations here, okay? So all the equation, please fully understand what the equation for, and what the condition for those equations. What are the applications you can use for those equations? Okay, for example, here, case 1, case 2, case 3. So what are the 3 cases? Do you still remember? So if you see a practical problem, you probably need to first thing to decide, hey, which case this problem belongs. Then I can find a equation to solve that. Otherwise, I don't even have a starting point. Okay. right? You see the whole picture of the class? Okay. You have many more equations later. Okay, so just be aware, okay, what you need to remember. Okay, let's come back to here. What is case one? Anybody remember? Don't look at the book. Okay, see if you remember.
Is that infinite length?
That's right. Case one is the easiest. It's the infinite length, okay? Easiest equation, but barely this case will be applied to any practical application. Okay, because you don't have infinitely long things, in reality. Okay, so maybe in some very special situation, you have a very long things, maybe you can apply this equation, but not likely. Okay, so what is case two?
Is it finite length with something at the tip with is it no heat loss or same temperature?
No.
Action at the tip.
I think case two is the most general case, right? Is that right? It's actually the convective. At the end, it is a convection condition at the end. Okay, it's a finite length, which means it's not too long. Okay, you think about it, if it's too long, then at the end, the temperature becomes very low. It's maybe just slightly higher than the ambient temperature, right? On the tip, maybe just slightly higher. The temperature decreasing in the thing. So if the thing is really long, it will decrease to very low temperature, maybe just close to the ambient temperature. So the convection to the surrounding ambient from the tip is very minimal. Okay, see my argument here? If it's long, the temperature at the end is low, so the convection heat transfer basically is due to the area coefficient HA delta T, right? So if your the tip temperature is close to the ambient temperature, there's basically no effect on the heat transfer through the tip. Okay, so you don't have to go through case two if that's the case. Case two is the most general or most complicated equations for case two. Okay, the reason we have to use case two sometimes is really the thing is short. Then the heat transfer through the tip, the tip temperature is still much higher than the ambient temperature. So the heat transfer, convection heat transfer through the tip is still noticeable. Okay, it is still significant. So then you cannot neglect the heat transfer through the tip. Then you have to go through case two. Okay, is that all right? Is my explanation clear enough here? Hey, since everybody's here, you made it to the class. I just want you to learn stuff before you leave, right? I don't want you to spend much more time after class. Learn all the stuff here. Discuss with me if you have any questions. Okay. Okay. So that's case two, right? What is case three?
Insulated tip.
Insulated tip. Okay. So that basically there's no convection heat transfer on the tip. So then this is actually equivalent to case two if case two is long. Okay, if case two is long, the end tip temperature is close to the ambient temperature, basically there's no heat transfer too. Then case two convert into case three. Okay, that's what I want to do usually. If I see if I work in industry, see a problem like this, I want to always try to see if I can use case three. Okay, case three is much easier like comparing to the case two. Look at this. I don't even want to write that long equation. Okay, it's longer the equation is, easier for me to make mistake, right? Okay, if we can use safe three safely, we use safe three. Okay, you insulated, so there's no heat transfer through the tip. Okay, insulated, so your heat transfer rate is 0 on the tip. Then lead to a small equation like this. And if case two, convection condition at the end on the tip. If it's long, then temperature difference is small. Then the convection through the tip is negligible. Then it become case two, become case three. Okay, so that will be better. Okay, good. So these are the three cases. Now today, before I give you the example, I wanna complete most of the theory of some equation, some more equation to give it to you. So the efficiency, thing efficiency, that's one thing is important to discuss. Okay, always when you design something, you always will ask, oh, is this thing efficient? Is that can remove heat enough, you know, to worth the money, right? So thing efficiency is our next topic. Okay, make it a little bit bigger. Okay. Okay, we use this letter eta for the efficiency. What does the efficiency really means? Okay, there's something called thing effectiveness. I'm going to talk about it in minutes. Okay, but let's do thing efficiency first. Efficiency, the definition is the actual heat transfer from the thing. Divided by heat transfer if the temperature on the thing is, if T naught is on the entire thing. Okay. It's a little bit weird when I look at it initially, first time, right? Okay, so you have a heat transfer for anything design. Okay, a heat transfer. Okay, what does that mean in the denominator? The heat transfer if the base temperature is on the entire thing. So right now, what's the temperature on the thing? Based on those equations, we know the temperature on the thing actually is decreasing from the base temperature. Okay, only on the tip, on the beginning of the thing, you have base temperature. Then the temperature actually decreasing along the thing. Is that right? So if the base temperature is on the entire thing, that's basically an ideal case. It's a kind of like a 100% heat transfer. You know, the maximum heat you can remove. Did you see the mechanism for the heat transfer from the thing to the surrounding? Because the thing temperature is higher than the surrounding. Okay, that's why you have a heat transfer from the thing to the surrounding. So the higher the temperature on the thing, you have more heat being transferred through the surrounding, through the side of the thing, right? Okay, so the maximum case is your thing temperature is the entire thing on the entire thing is the base temperature. Okay, that's the maximum case. In a reality case, you won't transfer that amount of heat because your thing temperature is actually lower than the base temperature. So that's how the efficiency is defined. Your current heat transfer rate over the maximum heat transfer rate for the thing. You're never going to reach that maximum ideal case because whatever thing you put it on it, the temperature will always decreasing along the thing. So the base temperature is always the maximum temperature on the thing, and in most of the thing area, you have a lower temperature. Right? Do you agree? Okay. So that's the definition. Okay. Is that clear to everybody? I think later I'm going to introduce the thing effectiveness. You'll see the difference about the efficiency and effectiveness. Okay. So eta F, right? It's the eta thing equals that equation 2.38. It's for case 3. You see, in this textbook, we always care about the case 3 because that's the case most of the time people use. Okay, for case 3, that efficiency become 10H. You can actually derive it, okay, based on the temperature value. Okay, but let's just look at the solution again here. Okay. So for case 3, is separate them. This is the definition. Okay, so you have an efficiency equation. Again, you have another equation, right? To me, heat transfer is easier. Basically, it's just a lot of equation. You need to know how to apply. Okay, you have find out the conditions. Okay. M. You remember what is M? Do you still remember? M is that coefficient, right? HP, square root of HP divided by Ka. So ML. Okay, I can rewrite it here. Do you remember this equation? Last time we introduced M, right? L is just L, the length, okay? Okay, so there's some simplification we're gonna make here, okay, for calculating M, okay? It's the P. Do you know what is P again? Okay, could you open your GroupMe? Okay, the picture I sent you last time. The sketch for a thing. Okay. Do you see that photo? Okay. So HK, right? HK are the coefficients. Okay. Doesn't matter. Okay. And the A is a cross-sectional area, right? What is P? What is P? Anybody?
Is P the perimeter?
That's right. Can you, based on the drawing I send you, can you give me an expression for calculating P? Anybody? I'm still waiting.
Would it be 2L plus 2Z?
No, it's not 2L plus 2Z. So before you can give me an expression, you need to know what a P is. What is the P we're talking about here? Okay.
Is it with the X and the T?
X and the T? No, X and the T. The parameter, look at the shaded area. Did you see that shaded band in the drawing? The blue, light blue colored band? That's a small element we're talking about, right? So the A and P are related to that band, right? Infinitely thin. You see, you put a dx here. Okay, x is a 1D direction, right? So for a small element in calculus, right, integration or derivative, we know that this dx is infinitely small, right? That's why I call dx. So what is the P we're talking about here? So that's important. You need to know those things before you can actually do a detailed actual calculation to solve a problem, right? Okay, I'd rather spend time on this to make sure everybody, all 22 of you here in the class, fully understand this. Okay, what is P? I just want you to give me the answer.
So kind of the whole thing, the perimeter multiplied the height is going to give us the area.
I'm asking the P. Okay, area. Yeah, you're right. Area, probably you're right. But let's talk about P first.
Is 2Z plus 2T?
I agree. Do you agree?
I do agree.
Look at the drawing. Okay, some simple geometry here, right? So your engineering student, especially if you are a mechanical engineering student, you really need to be good on geometry. Okay, your design basically always a 3D something structure or something. Okay, 2z plus 2t, that's the parameter, okay? That's the parameter of that infinitely thin band, okay, on the drawing. Good. Now, denominator A. I think one of you already said it, right? What is A? A is, yeah, it's the cross-sectional area of the thing, okay? So give me an expression.
Z times T.
That's correct. Okay, that's for the detailed calculation, right? You need to know those things. Okay, good. Now there's a simplification here. Okay, T is much smaller than the Z in most of the time. Okay, if you have thing like this, thickness of the thing usually is small. Okay, so what they do is they neglect this 2t term. Okay, so you can cancel the Z in the equation basically. Okay, neglect it because T is much smaller than Z. Okay, it's not what you want to neglect, then you can neglect it. It must be a justification. Okay, that's what engineers do, right? We try to simplify everything, okay, to make sure we can find a solution. Then, but when we simplify it, it's not just we can simplify everything. You have to have a justification, okay, make sure that works in reality, okay. Because of this, then the equation, then Z can be canceled here and here, okay. So the equation become a little bit simple. ML becomes square root of 2H over KT times L. Okay, that's one thing you can use. Okay, people commonly use after a simplification. Okay, indeed, it's very small. T is very small comparing to Z. Well, if that's the case, right? Sometimes maybe it's not. Okay, if it's not, then you better just keep T there. Okay, that good? That's one way to do it. Okay, some engineer like to use something called it's not me, okay? Some people like it. They call it the frontal area. Is that AM called frontal area? Profile area, okay. Okay. Profile area is the equals to L times T. Look at the drawing. What is L times T? What is the profile area? I already said the frontal area. That, to me, that's more easy to understand. Right? Frontal, the front area. When you look at the thing from the front. Okay. They call it the profile area. Okay. In the thing design industry, people, some of the numbers or some of the variable they like to use, for a long time. So they want to convert all those equations into those variables they are familiar with, they like to use. Okay, so frontal area is one thing in the thing design industry. So if you say frontal area or if you say profile area, people know what does that mean. Okay, AM is that's the front area of the thing. So if you use the frontal area in this equation, then ML become, you can just substitute there. It will become square root of 2HK times A front profile area times to L to the 3 half. That's the same equation, okay? These two are basically exactly the same. You just substitute this into this, it will become this, okay? If you used to use the profile area in the design process, maybe you want to pick this one. Otherwise, you can, if you know K, T and L, you can just simply apply this, okay? Okay, that's what I say. I'm trying to introduce many equations to you, and then you have to pick the correct equation for a particular problem. Okay, that's,
Dr. Why
yeah,
does the L have the raised to 3,
huh?
2? Why
It's
is
because
the
L, because if you want to move L inside the denominator, inside the root, it's in the denominator, right? If you times a, you become AM, right? T times L, then it's AM. So if you put one L in there, you're gonna put a half L here, L to the half outside. Did you see? If you multiply by a square root of L in the left term, you have to divide by a square root of L. If you actually divide by a square root of L, if you want to make L here, you're gonna take a square root of L here. Then it becomes the same thing, right? Or let's say this. You multiply by a square root of L divided by a square root of L. Are they the same? You didn't change the value, right? Is that right? So the divided by square root of L can combine with the first term, which just move the L inside the big square root here. It's L times T. Then become AM. But what's left outside is L times square root of L. It become L to the power of 3 over 2, 1.5, right? Is that all right? Do you know by multiply by the same thing in the fraction, the same number, square root of L divided by square root of L, you didn't change the value of the expression, right? And the divided by square root of L, you can move it, combine it with the first square root here. So the L basically going into the square root at the denominator. Then T times L become AM. And outside L times square root of L become L to the 3 half. Okay, that's just some magic in math. Is that clear? Is that right to you?
Yes, sir. Thank you.
Okay, yeah. So basically they are the same equation. Basically it's up to you to use which equation, okay? So depending on what you have, okay? If you have T or you have AM, basically, right? Everything else is the same. Let me get rid of this. Okay. This is the process. Okay, so this is the efficiency for case 3. Okay, how about case 2? Okay, we are trying to make sure many of the case 2 problems we can safely use case 3 to estimate. We don't want to introduce another equation for efficiency. Let's keep this efficiency equation. And if case 2, for case 2, the thing is long enough, then the end heat transfer on the tip is negligible, then we say, hey, case 2. We use a corrected length to representing the whole overall heat transfer length of the thing. Case 2. Let's say a corrected length. Okay, your length is L, right? So let's say at the end, on the tip, it's also heat transfer, also convection. So we can just flip the tip, flip the tip to the straight position. So it become half of the T of the tip. Also, let's count it inside as the fin heat transfer. So your fin heat transfer length is become a little bit longer, become a corrected length. Okay. So then use this LC instead of L for the equation, for the efficiency. So your efficiency is still the same equation. Tanh M times LC divided by MLC. Okay, same equation. that make sense? It becomes easier, right? You don't have to have a longer efficiency equation. Let's just use this. But it must be a condition. Okay, it must be a condition. Then case 2 can be simplified into case 3. Okay, the condition is this. Can convert into case 3. The condition is this: ht over 2k square root smaller than half. Okay. So basically, it's a convection on the tip. Okay. Relative to the heat transfer rate, the entire thing. You know, if it's smaller than a certain value, then we can safely consider it's a case 3. Okay. Although looks like it still have a thing, you're not insulated to the end. But if the heat transfer through the tip is really, really small, then you can neglect that and treat it as case 3. So this is the condition you need to check. Okay. Basically, you said, hey, if the t is really small, basically, right? It's smaller than half overall. But if the t is really small, the tip is really small, and the convection is not much on the tip, then it can be considered as case 3. This is the approximation, okay? And if this condition satisfied, the error will be less than 8%. As an engineer, we really can always do approximation, you know, make our life easier to get some solution. But you have to control the error. You have to manage the error. So you have to tell your client or your boss what is the error. If the error is less than 8%, okay, we're okay with it. That's what it says. Okay, so if this condition satisfied, your error should be less than 8%. If you use case 3 to replace case 2. Okay, and you use you change the equation a little bit, right? You're using the corrected length for case 2, right? Okay. So this check is important. Basically, it's not only for the efficiency, but also for all the calculation for case 2. Okay, for temperature, for total heat loss, heat transfer rate, everything. If this condition is satisfied, okay, basically you can just apply case 3 equations, all the case 3 equation for case 2. Okay, is that good? Hold on. Okay, I'm sorry. I have to sometimes pick a phone, see if it's my insurance company. You know. Hey, I heard that right now in Lake Charles, most of the people I know they have kind of conflict with the insurance companies. Estimate everything is not good. All my friends mentioned, is that true? Insurance, I haven't get the final estimate from insurance yet. Is that people are even finding lawyers, attorneys to fight for them? Yeah,
it is absolutely ridiculous. They don't want to do anything.
Yeah, that's what I heard. That's not right. That's why we buy insurance. You know, insurance is just work for the disaster like this, right? What the heck?
That's what they're supposed to be here for, but they don't want to pay. They're sending out-of-state people here. We had a woman come down from Michigan to inspect our house.
Wow.
And Michigan, she was not the best.
Yeah. See, might have a similar situation. The first adjuster came, he's from California. Okay. Then he counted my roof area is even smaller than the ground area, base area under the roof. You're an engineer, you know, right? Roof is like this. You know, the area should be like 1.7 or more times than the area in the bottom ground. The ground area is way bigger than the area they measured for the roof. How ridiculous is that? That's why I don't have the final estimate yet. I'm fighting for that too, you know. I thought I'm the odd one. I'm the only one. Now I talk to my friend. Almost everybody is fighting with the insurance now. Man, that's bad, huh? Okay. Yeah. Oh, I have a couple minutes. Okay, let me. Okay. So, any question on this efficiency? Is that good? So what I try to make is many of the case, in reality, you barely see case one. Okay, case one is probably out of the picture most of the time. But in reality, every case, everything is like a case two. Because case three is like insulated. Who will insulate the thing at the end? Nobody will do that, right? In reality, nobody, you don't want to see an insulated end. But the reason we have that case is that case have a simple solution, okay? Easier to apply. So all of the case actually in reality is case two, but 90% of them we can safely say, hey, it's close to case three, okay? Then we apply case three equation to calculate the thing, okay? Does that make sense? I think the book it doesn't say this clearly like this, but I'm just telling you with my experience. That's exactly what most people do. Most of the time you're calculating, 90% of the cases you're calculating by using the case three equations. But you need to make sure to check. That's why I will present this thing. It's important. Make sure it's way smaller than half for that equation, okay? So it will be safe. If it satisfies that equation, your error is less than 8%. 8% is sometimes is okay, but your error may be less than 1%. If the situation, you know, if the value for that equation is way below half, okay, way below 0.5. Okay, I guess that's it for today. The thing efficiency, that's what we covered in some review. Okay, next time we talk about the thing effectiveness. Okay, another equation I want to introduce. Then we'll go through some examples for the things. Okay, any questions? Is that good? I hope all 20, 22, 23 of you today will fully understand, comfortable with the idea of the thing, okay? So, okay. If you don't have any question, I guess that's it for today. See you on Wednesday.
Dr. Ning?
Yes.
Could you update the homework for fluids and heat transfer?
I already did it for the heat transfer. I will update some homework problem for fluids today before the class.
Okay.
Yeah,
Thank you.
Heat transfer, I put it into the same place. I forgot to mention in the class. I put it in the same place, just add 3 problems there. Okay, so go ahead. Now I recorded it.
Right.
Now, if you watch the video, you can still hear it. Yeah, I added the same place as the first set of the chapter 2 homework. Okay, I added 3 problems down there. Okay, yeah.
Thank you. Bye-bye.
You're welcome. Bye-bye.